Okay, so today, spiral. So I'll first talk about eddy currents and their relevance to different kinds of pulse sequences, and then we'll talk about spiral sequences. And I sort of introduced the idea a couple lectures back, but we'll go over it in more detail. And there's all different kinds of variations, and I'll talk about two interesting combo possibilities of spin echo and spiral and other different innovative ways for collecting data in K-space. So starting off with eddy currents. So when we take our trip over to the MRI center, we can sort of demonstrate eddy currents. So if here's the magnet like this, it's making a huge magnetic field, and so the magnetic field is sort of coming out like this, out of the magnet. That's the direction of the magnetic field, the B0. And a nice sort of physical demonstration of eddy currents is I've got an aluminum pie tin, so it's not magnetic. So it's safe to bring into the room because it won't be attracted to the magnet. But if you take that little pie tin like this and come up to the magnet with it, you'll find that it's not attracted to the magnet, but if you move it, it will suddenly resist movement toward the magnet or away from the magnet. If you just stick it in the magnet, it'll just slowly fall over like it's held up by nothing. So what's going on there is that the pie tin is filled with charges, tons of atoms in there and tons of charges, and it's a good conductor. And so what happens when you move charges in a magnetic field, that causes a current. So it causes a current to flow around the pie tin. Now, you might think, well, is that dangerous? Well, it's actually a lot of current, amps of current, but the voltage is very low, so you don't get shocked by it. But what happens is when those charges flow, they generate a magnetic field, and that magnetic field is kind of essentially pushes back against the main magnetic field. Now, you might wonder, what does that have to do with eddy currents in the magnet? Well, in this case, what we're doing is we're taking some charges and moving them through the magnetic field. But an exactly equivalent situation occurs if we change the magnetic field, because the magnet is made out of metal. It doesn't have magnetic metal in it, but it's got tons of metal. It weighs like 10 tons, so it's got tons of metal, literally tons of metal in it, and the gradient coils are changing the magnetic field, and so they're moving magnetic field lines around through the charges in the metal, which is the same situation as we have here, except sort of reverse, like you're moving the magnetic fields instead of moving the charges. And so what happens is whenever you change the gradient coils, it's going to essentially cause all these currents to slosh around in the actual metal of the magnet, of which there is a lot. And the important thing about these currents is that they're kind of long-lived. They sort of take a quarter of a second or something like that to play out all these currents. So it's actually quite a sort of a sluggish kind of response. And so what's the relevance to pulse sequences? So these are sort of well understood kinds of phenomenon, but we had this example like an EPI sequence where you're trying to do this. So if this is like, say, the X gradient, and I draw a pulse sequence that first we go to the negative side of XK space, and then we go to the positive side. Now, if you tell the gradient coils to do this, they they won't, they'll, if you put that current into the gradient coils, which is like negative current, in one direction here, and then, ramp to 0, and then go to positive current, what will actually happen if you actually measure the magnetic field that came out of the gradient coil? So you can put like a sensor in there and just actually figure out what did the gradient coils actually do. So what will happen is, when you're on the straight, it's not too bad. The measured magnetic field will be sort of about right. But when you suddenly go to a constant current through the gradient coils, you'll get something that actually looks like that. There's kind of sort of an overshoot. And what's causing that? So, what's causing that is the, eddy currents. And the eddy currents are basically from putting current into the gradient coils, creating a magnetic field, and then that magnetic field changing, the change in the magnetic field relative to the charges that are in the steel of the magnet. And so this is well known that it doesn't do what you told it to do. And so there's a whole complicated system in there called eddy current compensation. And what it does is it attempts to essentially compensate for that. And so what it will do is it will put something, it will take, this is what you asked for. So this is the desired. So in your pulse sequence, you program that. And then what the magnet does is it says, oh, I know you want that, but if you actually did that, you would get this, eddy currents causes, overshoot. So in order to fix that, we will, what actually comes out. So this is, what actually is sent to amplifiers. And so the end result is you'll get something that looks like the green curve that will. So this is, and there's all different kinds of, there's various orders of corrections here. It's a complicated thing. You need derivatives and second derivatives because, like how characterizing, how the eddy currents actually behave is not straightforward. And so there's hours of calibration to try to sort of guarantee that you get something that actually looks like one of those sharp edges. So this is relevant. It's kind of, the badness of it is in proportion to how big the gradients are. And so whereas this a particular problem, it's a particular problem for something like diffusion imaging, which we'll talk about next week, where you're trying to image the microscopic, like a hundredth of a millimeter diffusion of water in one direction or another direction. And the way to do that is, the basic way to do that is you turn a huge gradient on, wait for some diffusion to occur, and then turn a huge gradient on in the opposite direction, and then record some imaging. And so that involves like the biggest gradients that you can muster, and because of that, you're going to end up with lots of eddy currents, and the eddy currents are going to cause image distortion because your reconstruction is assuming that you put in perfect spin stripes, but the eddy currents are obviously going to mess up your spin stripes. So that's what eddy currents are, and they're always there. And there's attempts to compensate them, and then there's also, like I said, there's also companies that are starting to market probes that will actually, that can be built into the head coil that will actually measure what the magnetic field that was generated actually was. And so one thing you could do is you could try to sort of do eddy current compensation and sort of fix up the gradients. But the other thing you could do is, okay, we told you to do this and you didn't do that, but what did you do? And so you could just actually measure what the magnetic field was and then feed that back into the reconstruction. And so there's multiple ways to sort of fix this problem. Okay, so any questions about eddy currents? So there's all different kinds of software for trying to fix eddy current caused distortions in diffusion imaging, because a lot of times as you change the direction of your diffusion gradients, that's going to cause the spatial direction that the brain is warping in to change. So, okay, eddy currents. So we'll definitely go over to the magnet at the end of the quarter and play with the eddy currents. Okay. So now let's talk about spiral and all the different kinds of spiral. So almost all the sequences that I've talked about so far are kind of rectilinear, like they go across k-space in the x direction, or they go across k-space in the y direction, or maybe they go diagonally down to the corner and then go back and forth. But there's no particular reason you have to do that. You can sort of go any direction you want to in k-space just by turning on gradients. And in 3D k-space, you can literally just sort of go anywhere in 3D, just turning on the gradients, if you turn on all three gradients. And it turns out that kind of output from the amplifiers is actually kind of friendly to the magnet, because it's actually quite hard to make like a really sharp edge. It's much easier for the magnets, for the gradient coils to generate sort of curved trajectories in k-space. It's kind of more natural, because you've got a lot of weight in there, and it gets easier to just kind of like move that weight around in circles than to sort of suddenly go like bam and then turn it in a different direction. So it turns out some of the eddy current compensation isn't perfectly adapted to spirals, but the big advantage of spirals is that you're turning on 2 gradients at once or 3 gradients at once, and that means you can go faster through k-space. And also because you don't have any sharp edges, that allows you to go faster. How much faster? You could go like 4 times or 8 times faster, a lot faster. And so this could potentially speed up your acquisition, and depending on what you want to do. So what's like the absolutely simplest spiral sequence? Just we'll say a spiral gradient echo single shot, like EPI. So like in EPI, you do 190, and then you record the whole, you record all of the data for one slice. So the idea is to use a spiral to record all the data for one slice with just one 90-degree pulse. And so what does that look like? So you have an RF pulse, like a 90-degree RF pulse to tip some spin. So there's 90, and then we could select a slice. So we could still sort of do a rectilinear slice. So here's our select a slice. So when I write these Gy, Gx, in real life, if you've tilted your slice, you're going to have like multiple gradients on. And so this is when you're actually running a sequence, the slice select might be spread across several gradients. And so this is just sort of writing GZ, GY, GX is just kind of a mental way of simplifying that picture, not having to worry about what actually happens when you run a pulse sequence with tilted slices. So there we've selected a slice, and then we turn on the gradients. And so what does that look like? What does that look like in k-space? So if we start right at the middle, we don't have to go anywhere. Let's just start right at the middle. And then what we do is we turn on both gradients at the same time, the y and the x gradient. So normally we think of the x gradient as the readout gradient and the y gradient as the phase encode gradient, but the readout gradient is just another way of doing phase encoding in a different direction, so we can turn them both on at the same time. And so what we can do is, let's see, so we'll put like something that looks like a negative sign on this one. It's kind of going further and further apart. And then we'll put one that looks like a cosine on this one. So here's, this guy looks like a cosine. So let me just line these up. So this guy will be cosine, so okay, something like that. Did I get it right? Yeah. I'm going to do it one more time. Put my target off by 90 degrees marks in there. Okay, so that's where we were, but we want our peaks to be here and here. Okay, there we go. So we'll do our cosine. There we go, that's better. Okay. Okay, so what's the plan here? So the plan here is that the distance between these two peaks, should be, pi over 2, 90 degrees. And so what does that do to our position in k-space? So what we're going to do is, we'll basically on the x gradient sort of go out toward the right, and then on the y gradient go down, but then before long we're starting to go back up again. And then if you just work that out, you'll see that what you do is you just sort of go around in a circle like that, as long as these guys are always like a quarter cycle offset. So and so why does it spread out? Well, over time you're going a larger distance, and so if you want to sort of go if you basically want to go at about the same speed through k-space, you need to sort of spread out the little sine waves. So what happens when you record? Well, there really isn't an echo, per se. So what happens, you do this RF pulse and there's a big FID that you don't record, but then as soon as you start recording, there's a signal coming out. It's bigger at the beginning because you're in the center of k-space, and then it just keeps going. So there really isn't any echo, which is kind of sort of a little disturbing when you first hear about this, but you just basically record all of that data. So, starting here, just record, all of the data. Now, there's a problem, is that it was on a spiral, and we need the data back on a grid, and so, we have to do, regridding, what it's called. So, what we want is we want our data to be like on a rectilinear grid, so we've got to interpolate this data. So say we recorded a data point here, but it needs to be to this grid, so we need to interpolate the k-space data, back onto the grid, because we just recorded at those arbitrary locations in k-space that aren't right on the grid. So once we've done that, then you can just do a regular old inverse Fourier transform to make your slice. So this is the phase. This is this is a 2D one, so that actually is the slice direction. This is the phase encode gradient, but you can see it's not really any different than the readout or the frequency, readout frequency encode. They're basically the same thing. So what's the advantage of this? You can go really quickly, and for a given amplifier power, you can go more quickly. And so some of the first fMRI pulse sequences before they got the amplifier power up were done using spiral because you have a better sort of amplifier to gradient movement ratio. But now that we've got super powerful amplifiers, we can go really, really fast. And so an example, when I was back in London, there was somebody trying to image the articulators when somebody's actually, like the glottis and these very rapid movements down there. And they managed to get with the spirals, they managed to get a frame rate of about 50 hertz, 60 hertz. So 60 images per second. So you could actually image what's going on when you're saying, making noise. So if we were trying to do fMRI with this wouldn't be very good because we're starting in the center of K-space. And so what is the effective TE? The effective TE would be very short, like this. So this is, TE in quotes, because there really isn't any echo, TE effective. But what do we mean by TE effective? We just mean like, it just means like, time from RF to record center of K-space. And so that would be too short. That would be too short to get any T2 star contrast if we were trying to do EPI, because we would basically be recording like, here's activated brain and here's, not activated brain. And so if we record right at the very beginning, it's not going to work. So we want to go out, somewhere later. And so what you could do is you could record that anyway, or you could just go out to the edge of K-space. But since we're going to get out there anyway really quickly, then what we could do is basically just spiral inward. So you could use, the gradients to spiral inward, so you would then record, the center of K-space last. So this is, this is there's in-out spiral, and here's, out-in. And so in that case, the effective TE would, in that case, what would happen is the signal would be decaying, but as you went to the center of K-space, it would be getting bigger, and so you would sort of get, the signal would increase as you headed toward the center of K-space. So you can do functional MRI with spirals like this. That's not a problem. So that's spiral. So any questions sort of about the very basic, before we go off the deep end? Sort of the basic spiral idea. K-space for slice. So this is a 2D. This is a 2D spiral gradient echo single shot. And we have these. We have these on the scanner. So what other kind of things can you do? So once you've done this, well, like, why do we have to just do a spiral? Couldn't we do something? Couldn't we do some other fancy random way of going through K-space? And actually, before I talk about those other random ways, let me just talk just a tiny bit about how you kind of calculate, how you go back and forth between this K-space spiral and, what gradients do you need. So we talked a long time ago about when we first had this K-space idea of gradients moving where you are in K-space. And so the idea was you integrate the gradient, over time, And sort of like the area under the curve of the gradient tells you where you are in k-space. So that's like going from this way to this direction. So, you know, you can say, like, I did this to the gradients, I just integrated, find the area under the curve up to a certain time, and that tells you where you are in k-space. But alternatively, if you take the derivative of both sides here, if you want to go the other way, you know, then you can say, here's something I want to do in k-space. And so if I take the derivative of that, you know, it's the rate of change of that thing, then that's going to be equal to the gradient. So you can, so the equation, the picture, I have the equations that sort of demonstrate this in the reading if you want to sort of look at how it works. But you know, that way you could sort of say, I want to do this thing in k-space, what gradient do I need? And then this will tell you what the gradient you need is. You can get an equation for the gradient. So what are some of the different ways of, you know, going through k-space? So we could do you know, constant angular velocity. The equations are in the reading. So angular velocity in k-space. And what, if you go through the equations you need, what do you need for that? You need something that looks like, you know, on the x and the y gradients. So here's the x and the y gradients. G, y, g, x. You need something that looks like basically something like that. So, you know, one will be look like a cosine, the other one will be a sine. And that will basically take you through k-space with a constant angular velocity. Now, the bad part of that is that when you get out to the far parts of k-space, you're going really, really fast. And so that means that your bandwidth will have to go up, or you have to have a very high bandwidth, which is generally sort of a lower signal to noise if you're going super fast. And so alternatively, what you could do is a constant linear velocity. So if you do a constant linear velocity in k-space, you get a different set of equations for what the gradients should look like. And what those look like, they're like the ones I drew there, more or less. So the gy and gx, they look like, you know, something like spreading out like that. So the problem with these is that you're going really fast. The gradients are getting very vertical right at the center when you've got to like go around really quickly. And then as you're going the same speed through k-space, you know, along the spiral, then your gradients can be less packed. And so usually in practice what people use is something that's kind of a combination of those two. So like start off at constant angular velocity and then end up at constant linear velocity. And so you would get some gradients that, you know, look like something like that. So that's like start gx. So that guy is like start constant angular, and then end constant velocity. So you can see there's all different kinds of, you know, little hacks we need to do to sort of make this work well. But people have worked this out up in Stanford. There's a lot of spiral people up there, and actually at UCSD, there's a lot of sort of interest in using spiral. So that's sort of regular spiral, but what about, let's just like, go crazy. So what about, doing some other path through K-space? And one of the guys who invented MRI was maybe partly sort of influenced by the way that CAT scanners work, was going through K-space in a radial direction instead of kind of the opposite of a spiral. So, going from the center out. Now, one thing there is that if you do that, you'll record the center of K-space multiple times. So it's kind of, in some ways, you could argue maybe a little wasteful to record it so many times, although there's several reasons why you might want to do that. So one thing we could do would be, radial, and we have this on the scanner too. So the idea is you turn on both gradients at the same time so that you take a diagonal line through K-space. So you could turn on both gradients, and then when you get to the end of edge of K-space, you could make a turn and then come back through K-space this way, and then you could make a turn, then come back through K-space that way, and then make a turn. See, so you could do something like that, and sort of cover K-space going through the that's one way of doing it, going through the center multiple times. You could do something that's sort of like a combination of EPI. It's another one we have on the scanner, where you essentially pick out like a little band in K-space and then go back and forth like that, just like EPI, except like tilted EPI. And then pick another band. So let's pick another band like here. And then go sort of back and forth this way. Sorry about the squeak. And that one is called propeller. I don't know what that stands for. Propeller or blade. I think there's several different versions of it, sort of propeller and blade. Now this time you're recording the center of K-space a lot. And why might you want to do that? One reason is that you might want to use some of that data for motion correction, for instance. So in particular, if you're imaging something that's moving, like you're trying to image the lungs, and the person obviously has to breathe in there, you could try to make them not breathe for a while, like breath hold, like hold your breath, we'll take a scan and then let your breath out. But you could let them breathe normally, and then every time you go through the center of K-space, because this is quite quick, we could sort of calculate like what movement occurred and then factor that in and sort of fix up the scan. So that's an example of why you might want to record the center of K-space multiple times in order to calculate movement and then actually feed it back into correct movement, like of the diaphragm. What about another sort of, there was this old child toy when I was growing up in the 60s called Spirograph. It's a bunch of gears and with a little pen, and you could sort of make all these different little sort of atom-like pictures. So what about just turning both gradients on? What's the fastest way to get through K-space? So spiral is kind of hard because you got these sharp edges at the middle, and then you're going too fast around the edge. But what about if you just did like a 1960s atom? So you went through K-space nice and smooth and curvy. And I can't remember, I think these ones are called starburst. That's the fastest way to get through K-space. Because you don't have any sharp edges. And so you could do like a very, very rapid, so I don't know, what is that one called? It might be called starburst or something. They have all these names, starburst. But why stop there? Because actually, you've got 3D, and so what we should do is turn all the gradients on full blast all the time. That would be the fastest, absolutely fastest way to collect the data. And so I'll talk about a couple 3D sequences after this in detail. But if here's your axes of 3D K-space, then why not just turn all three gradients on and just go around through 3D K-space? Or why not do some kind of compressed type of imaging where we just go to sort of random places in K-space and try to fill in the rest? That's another kind of strategy. Yeah.
Could you undersample something like that, or is the undersampling just coming in the voids of where you're not going?
No, you could definitely. So the question is, can you undersample? Definitely, you can undersample. Yeah, and like any kind of compressed sense type thing is going to be undersampling, and then try to, use like an inverse type approach to, fill in the missing pieces, or a grappa-like approach where you do one scan that has all the lines to try to make a little kernel that will allow you to predict what the missing parts are. You can definitely do that with this. Yeah, that's where all the sort of action is, trying to sort of make super optimized sequences that run really quickly and are undersampled, definitely. So let's talk about two actual sequences, where all hell breaks loose. So the first one was a very cool sequence that Eric Wong at UCSD wrote, and I ran this back in the day. I should have done more. So one of the things about spiral is that, I'll talk about this next week, is that the distortions you get in spiral are different. So spiral, I always phrase this as spiral has a marketing problem. So the distortions you get from spiral are fundamentally different than what you get from something like echoplanar imaging. So with echoplanar imaging, what happens is, just in a nutshell, it takes a long time to record the data going in the y direction in K-space. And whereas you're recording the data very rapidly as you go back and forth. And so what happens is you get distortions that cause like a shearing, like the brain will come out sort of shaped like that. Something like that is the kind of distortion you get, but it's sharp. So it's distorted but sharp. So what happens with spiral is that as you're going through K-space, the distortions you get have to do with the fact that the angle of the stripes you're stamping on as you go around in spiral are slightly off. And so what happens here is you tend to get a blur. Now, so this is, distorted but sharp. And so people like this a little better, even though it's, I would say like it's better to just have a blur than to have some distortion that sort of looks overly sharp, sharper than it should be. So this is EPI, and this would be a spiral. And so we'll go over why that is. But because you get a little bit of a blur, people have said, well, it doesn't look quite as good. It's not quite as sharp, and so I'm gonna stick with this one that's distorted but sharp. So I think that that marketing problem has essentially made spiral less popular than it should be. So this pulse sequence I'm going to talk about is it's a stack of spirals, 3D inversion recovery, fast spin echo. So you can see, how you can sort of like tack tackle multiple, that's what happens now in pulse sequence development. You say like, oh, I got this little sort of module or it's a weird way of doing something, and I'm going to sort of tack that onto some other pulse sequence that I kind of know about. And so how does this work? So, and what's the use of it? You get like unbelievable contrast, incredible contrast. So let's first just talk about the overall picture of what I'm going to draw before I go into the horrible details. So with an MP-RAGE, what happens is we've got this. So this is basically a structural scan, a high-resolution structural scan. So an MP-RAGE is another high-resolution structural scan. And what does that look like? That looks like it's this weird non-steady state thing where we start up at MZ0 here, do an inversion, and then wait a while, and then we have a bunch of alpha pulses, and then hopefully when we get to the center of K-space, there'll be another tissue type that's recovering, and that guy will be at 0, and this guy will be not at 0, and we hope that, we go through the center of K-space. So this is, where we go through the center of K-space, but it's kind of a screwed up scan because you're recording different spatial frequencies with different contrasts. And so it's not a steady state. You're not in a steady state scan. So then we go there and then, wait for a while until we invert again, etc. So that's an MP-RAGE. And so what is this spiral one? This one's a gradient echo, but now we're going to do a spin echo. And generally a spin echo would be preferable because we correct for B0 defects, T2 instead of T2 star, less distortion. And so we start off with the 180. So this is our spiral 3D inversion recovery spin echo, fast spin echo. So how does this work? So in this case, we just wait until we get all the way up to where we want to. So here's the two tissue types that are recovering. So that one recovered, and this guy didn't recover as much. And then at that point, instead of doing these little alpha pulses, so these are the little alpha pulses, we just do a 90. So right here, just do a 90. And so now we have a nice clean signal that we're only getting magnetization from this 190, and then we do fast spin echo here. So fast spin echo. And so what does that mean? That means then we do some 180s in there, a whole bunch of 180s in there. And so the advantage here is that we do a 90, and then a 180, and then record. So in between each of those 180s, there'll be an echo, and then eventually we wait for a while and then do it again. So that's kind of the overall picture of what's going on in the sequence. And so what does it look like? So start off with a 180. And then wait quite a long time until we do our 90. So here there's quite a long time in there, and then we do our 90. So we would have to select a slab for that guy. Sorry, wrong kind of slice select. Have the ears one, yeah. So we select a slab for that guy. And this guy is a 90, and so we'll do a regular slab select there. And now what we do is, so this was the preparation one. That's the initial inversion for the inversion recovery. Now we wait until we recover to that middle point and then do a 90. Now we have to do a 180 to make our train of echoes. So now here's our spin echo. So it's inversion recovery spin echo. So there's two different kinds of 180s. The one that sort of does the inversion to get the contrast, and then the 180s that make the echo train. And so now we have a bunch of 180s here, and so we have to slab select those guys. But it's a 3D scan, and so what do we do now? We do a stack of spirals, and so what does that look like in K-space? So here's our K-space. So the idea is we do, one spiral up here, and then at some later point we do. So if this is the KZ direction, for a different setting of the KZ gradient, we do a spiral in a different place in KZ. So here's another spiral. Oops, went the wrong way, but yeah, let's go the right way. Okay, better. So we do another different KX, KY. So it's a stack of spirals, but not only that, it's just like you can't quite get all the way through high resolution K-space, so you have a stack of interleaved spirals. And so if we collect sort of part of the data there, and then next time we come around and sort of collect the data that's in between, that's how you would do it. So it's, interleaved leaved spirals. So what does the pulse sequence look like? Well, we have to sort of tack on, our all the different partition directions here, like that. That moves us up and down in K-space. And then we have our readout, and the readout is the spiral readout. So that moves us to a particular part of K-space. Then we wait for the echo. So we wait to where everything sort of comes back into phase right there. But even before everything comes back into phase, we start recording, and so there'll be some spiral gradients on the X and Y. So here's the spiral gradients. And then sort of record all the data from one spiral layer there. And then we do another 180, because it's going to be an echo train. That's the fast spin echo part. And so here's another one of those 180 type slice select pulses. But it's fast spin echo, and so we have to fix. So at this point, we've got to sort of fix wherever we ended up in K-space. Like, that's the whole idea of fast spin echo. We record an echo, and then we sort of put everything back so that we can record another echo from the same 90. And so this is the so this, if we went up there, then we have to sort of like fix there, and then we also make sure that we fix wherever whatever we did. So there's a fix here. So this is to fix so that we're ready for the next recording, because we're not sort of trying to get rid of the magnetization, trying to save it. And so then we, then you'll wait the same amount of time and then do another one, all from that 190 that just was nicely placed right at the center, right at the moment when you crossed over the 0 point, so you get a huge amount of contrast between, say, white matter, which is recovering quicker, and gray matter. And so, you would have like some more spirals here, and some more of these here, etc. And so you could record, record a bunch of, maybe 20 or 10 or 20 spirals here, and then do the ones that are in between. So what's the bottom line? So the bottom line is you just get like staggering gray-white contrast. When I saw this, Eric sent me the scan, and I put it up on my monitor. I couldn't see the gray matter. The gray matter was so much contrast between the gray and the white matter. It looked black. All I could see was the white matter. So if you look at a regular MP-RAGE, what do you get? You might get, depends on how you normalize it, but you might get, say, the white matter. So here's MP-RAGE. So the white matter equals, value might be 110, and the gray matter might be 90, something like that. So you might get 10% contrast, 15% contrast might be, say, 105. So that's a typical contrast. If you just take the percent difference between these numbers. And so what did this spiral 3D fast spin echo look like? It came out, so the white matter number was it was a signed sequence. I didn't go over why that is, but it was a signed sequence. So the white matter came out at 200, the gray matter came out about 0, and the cerebrospinal fluid came out about like -50. So it's like staggering contrast. If you just make those all positive, it's like, instead of like 5, 10%, 15% contrast, it's like 200% contrast, just like gigantic contrast, 150% contrast. So, and just nobody's really used this. And for scientific purposes, having that much contrast and very uniform contrast and spin echo distortion corrected contrast is a really good thing. What's the downside? Why haven't they used this? Well, one thing is a little blurry, and so people are kind of discriminated against it because it looks a little blurry. Another reason is there's so much contrast. If you gave it to a radiologist, they would say, I can't see anything in this thing. It's too much contrast. But if you're trying to make quantitative measurements, something like this would be very helpful because you've got such a large amount of contrast between the different tissue types. So that's a interleaved stack of spirals, 3D inversion recovery with fast spin echo. So what's another one? So last night I was preparing for lecture, going through my notes, and I thought I would look up a few spiral-like sequences, and so I came across this paper from a couple years ago. So if you want to look it up, here's the paper. It's Schwartz et al. 2018, magnetic resonance in medicine. That's one of the main journals. 80, 24, 27. So what is this? So this is a way to try to record something that's like an MP-RAGE, but really quickly. And what's really quickly? Like 40 seconds. So normally, like an MP-RAGE will take the minimum of something like about 5 minutes for a high-resolution one. So what is this one? So it's a Wave-CAIPI grappa inversion recovery MP-RAGE. So what are all those things? And how can you get a high resolution scan, like a 1 by 1 by 1 scan in 40 seconds? So basically what it is, if you look at the pulse sequence, so there's a 180 because it's like an MP-RAGE. You do an inversion at the beginning, and then you do your RF pulses. And what the pulse sequence looks like is the readout gradient. You just turn that one on. So basically, we just you know, go to the left side of K-space and just turn it on for the readout. And then for the phasing code gradients, what you do is turn them both on with spiral-like things. But before we turn them on with spiral-like things, we go to some place in K-space. And so these are like all our phasing code things. But after we've gone to that place, we, in addition, turn these guys on, like sine waves. And until we finish the readout. So what does that do? What does that do? So why is it called all those things? So what happens, what do you get out of it? Well, as you go through the center of K-space, you get something that sort of looks like an echo, but there's, a bunch of little weird things going on because of how you're messing around in K-space. And this is an undersampled scan. That's the grappa part of it. And so what does that do to you in K-space? And then you repeat. At this point, you just repeat for another combination, another gradient combination. So what this does is, I've never drawn this before, so this may or may not be interpretable, but I'll try to keep it reasonable. So we start at the center of K-space. So here's the center. So here's the KZ and KY and KX. So we start at the center of K-space, and then let's make that less so I don't get in my own way. That's KX there. So we start at the center of K-space, and then go down to the corner here. And then, so that's done by turning on both of these, picking out, say we picked out, to go to the bottom corner, you'd have to pick out like a -1 here and a -1 here. That would stick you down in the bottom left corner. And then we turn on all three gradients at once. So what are these two gradients they're going to do? They're going to make you go through little corkscrews in K-space. So basically, they're going to head across K-space, head this direction, but in a corkscrew-like fashion. So they're going to go like, say we'll go this way. So they're going to go this way, sort of corkscrewing through K-space, along a little tube like that through K-space. So here's like one little tube through K-space. And so then what's the CAIPI thing? So the CAIPI thing, this is like sort of zigzag, blip up, blip down. Because remember when we talked about multiband, on the Z gradient, what you did, you went sort of like an upward blip and a downward blip, and that caused it kind of caused the slices to be unoverlapped. And so you do that here, but except what you do it with where you put the spirals. And so there's kind of like a zigzag in K-space where you're putting the spirals. So like the next spiral will sort of be over here, and it will be in a tube over here where you're going around the tube, and then the spiral after that will be over here, and you'll be going around the tube like that. And so it's an undersample. And so what is this? Here's the zigzag. That's the CAIPI part. It's going to the center of those guys. So that guy's the CAIPI part. It's undersampled because you're not filling up the entire K-space, so you've got to do some kind of calibration scan at the beginning to try to figure out the little kernel that will allow you to sort of fill in the missing data. So it's a grappa type scan that's undersampled. That's why it goes so fast, because you're not collecting all the 16 million data points in K-space. It's an inversion recovery, so it has a good gray-white contrast. And then this part here is the wave. The little wave is the corkscrews. So this is, but what's the advantage? You can get like a 1 by 1 by 1 scan in 40 seconds. And so that will allow you to do much higher resolution scan. So if you take 5 minutes, then you could do like, a scan with much smaller voxels, because you could collect sort of more of undersampled K-space. So that's where we are. So if you go, this is the kind of paper I want you to go and bat your head against in the literature, like just read one of these papers. You can sort of, you don't have to understand the whole thing. The idea is you just go in there and just say like, yeah, I remember there was something about this zigzag business, and I remember there's something about, something about spiral, that's two gradients on at the same time. So it's not really a spiral, it's kind of a spiral little corkscrews. It's not going through, large parts of K-space, it's just going through these little chunks of K-space, but it combines the grappa idea, where you undersample by first collecting a fully sampled chunk of K-space somewhere, so that you can actually make the little weight table that will allow you to sort of fill in the missing points. Because sooner or later, you have to fill in all the points so you have a full 3D K-space that you can do an inverse 3D Fourier transform. So slowly but surely, the physicists are just hacking away, trying to sort of like speed things up even more than they already are speeded up. And this could obviously potentially be useful if scanning kids. They're thrashing all around, so you could do like 5 of these in 5 minutes, and you pick out, there's one in there that was where the kid was reasonably still, and so you could actually get some good data out of it. And so they're always looking for a way to speed up, especially since a lot of people have trouble staying still. Okay, so any questions about the Wave-CAIPI grappa inversion recovery MP-RAGE? So, all good. What's that? Oh, yeah, right, sorry, MP-RAGE. There we go. Yeah, MP-RAGE sort of, incorporates the idea of inversion recovery, so it's, I think it's MP-RAGE. I think the, sorry. I think MP-RAGE means rapid gradient echo. So it's magnetization prepared. That's the IR part, and then rapid gradient echo. So it's not as morally upstanding as the stack of spirals, because it's got this sort of different contrast for different parts of K-space, problem. But who cares when collecting the data in 40 seconds? So, okay. Yeah. So I mean, part of the goal of this class is not to allow you to completely read these papers and understand every bit of it. It's just to understand it well enough so you get the general gist of what's going on in the paper. And you can sort of see what's coming down the pike, because sooner or later somebody's going to make a nice pulse sequence and the scanner company is going to buy one of these software companies that's making this pulse sequence, and then it'll appear on the scanner, in a couple of years. Okay. No other questions? All good. Okay, I think I'll end there, way over time.